Hi guys, good afternoon. Can anyone confirm that you are able to hear me and you are able to view my screen as well? All right. Guys, can you see my screen? Just confirm so we can start. Okay. Okay. Thanks, guys. Thanks for confirmation. I hope everyone is able to view the screen and able to hear me, right? So guys, welcome back to the series of NLP. And today's topic going to be very special. Today we will be starting with first word embedding layers. Okay. So we'll try to understand how to implement the word embedding using the Keras. Okay. We yesterday discussed what is the word embedding, how is the word embedding taking place, what is the entire concept behind this word embedding, right? And we try to implement this use case today using the Keras. And then second topic for the day will be LSTM neural network, recurrent neural network of LSTM. We'll try to understand the entire intuition behind LSTM, why LSTM exists, what are the challenges in the recurrent neural network because of which we were able to see recurrent neural network yesterday. We've seen what is the neural network, what is the operation performed in the recurrent neural network, what are the challenges, why vanishing gradient problem existing, why there is an exploding gradient problem, and how to tackle them. And in order to tackle them, they gave a birth to a concept called as LSTM. Okay. LSTM is there, GRU is there. So it's going to be very special today. I will be showing you 3 use cases today. One will be for how to classify the fake news using the Keras again with the LSTM. And then if time permits, I will also try to show you bi-directional LSTM. Not time permits, I will compulsory try to show you the bi-directional LSTM. We'll try to also understand what is sequence to sequence. Okay, sequence to sequence architecture in the NLP. And for that reason, we'll try to understand the entire structure behind the transformers, that is encoder-decoder. And I will try to make a walkthrough for the, guys, stacked LSTM also. I will try to show you. And I will try to make a code walkthrough for encoder-decoder as well. We'll try to understand what is the difference, how the complexity increases, what are the challenges, how we can make it more complex, more comprehensive, and how we'll be able to get to the closer side of the high-end solutions. Okay, that's the pretty much agenda, guys. So let's start with the recap of understanding the LST. Before even LSTM, let's start understanding the word implementation using the word embedding. Okay. All right. So let's have a simple recap that what will be the first process when we're talking about the text pre-processing, right? In text pre-processing, in what is my life cycle? First, I have to declare my vocab size, right? Once I declare my vocab size, let's say 10,000 for that reason. So whatever data I'm receiving in terms of these sentences or paragraphs and entire corpus of the data, what I will do, I'll try to tokenize the data, tokenization, right? Once I do a tokenization, I will be using stop words, punctuation marks, and some other relevant, let's say any special character, all those will be removed. Then I will be performing stemming as well as lemmatization, right? Lemmatization technique will be used. And after that, I will try to convert them, this entire clean data, whatever clean data. And also we will be using the upper or lower cases for that purpose of the converting data, right? And once I able to clean everything, then what will be the next step? Whatever the clean data frame is there, I will be using word-to-vec techniques. And we have seen that what are the challenges in the traditional word-to-vec techniques like PF, IDF, bag of words, or for that purpose, scriptgram, CBOW, everything, right? We were able to understand. So today's challenge is, or today's understanding is all about how we're able to convert this entire clean data into the numerical form using something called as featureized representation, which in fact we saw. We were in lot hurry because we took this session in the end of our lecture. So we were able to understand that what are the challenges, like there is a high dimension, and there is a sparse matrix. Sparse matrix means whenever I using the one hot encoding, I have to convert the things, right, into the vectors, and then I am storing them as indexes, these words, right? and then using which I was able to end up with 10,000 dimensions. And whenever I am trying to represent them, I'm trying to represent them using 0, 0, 0, zeros and ones, which is creating me the dense sparse matrix and dense, not dense, sparse matrix and the high dimension. So by using this Keras, right, using the Keras, I am trying to do a word embedding, which will help me, in fact, this way to achieve a dense matrix and low dimensions. Okay, so low dimension, whatever 10,000 dimensions were there, we were able to bring them towards, let's say, 100 dimension. And once, if I am able to convert them into a dense matrix will be something called as, which is showing like 111. In this case, if you see this matrix, this is dense because it consists of less zeros and more important values, and using which we were able to also understand the similarity, right? Word similarity, like there is a similarity between man and woman, king and queen, right? And on the basis of that, on the basis of this kind of features like lively being, human, gender, royalty, verb, ruler form, all these things, we were able to connect them. We were able to show them in featurized way, and we were able to bring them into the lower dimension. And when we try to plot them into the 2Ds or 3Ds, at that time, we will be able to also understand the similarity between the words and how we can identify the similarity between the words in order to make the sequential processing of the data. So let me switch to my notebook and I will try to show you the implementation, how we can create a word embedding using the Keras. Right. So let me share my Jupyter. Can you guys quickly confirm me if you are able to follow my Jupyter? All right. Okay. Thanks, guys. All right. Let's get started then. Okay. How to perform word embedding using the Keras. So for Keras, the background will be TensorFlow, right? Background we'll be using TensorFlow. And for the purpose of the Keras, what I have done is I have taken a TensorFlow more than 2.0. And there is a small difference like in the TensorFlow 2.0, 1.0 and 2.0 is whenever you are calling this Keras library, at that time you have to call first TensorFlow on Keras, and then if you using greater than 2.0 series, then there will be some sort of ease when you trying to call the Keras. That's the only difference. Also in TF1, every operations is performed session wise. There are different session in session.run and session. All these things. I don't want to go into the details, but just trying to tell you what is the difference, that everything runs in sessions in TF1, wherein in TF2, TensorFlow background 2, everything has to run without this session. So it reduces the complexity. Overall meaning is that it trying to reduce the complexity and making our job easier. So that's why we are using TensorFlow 2.0. I have first installed TensorFlow 2.0. If you want to perform the same operation, you'll have to install using pip install TF2. Okay, pip install TensorFlow 2.0. And then from there, what we have to do is we have to import the Keras. And from Keras even, I require one hot encoding for text pre-processing, right? And then I will also try to show you how we're using the embedding layer. There's a special layer called as embedding layer. Using this embedding layer by giving certain parameters, like what is the maximum sentence length, what are the dimensions you are looking for, and what is your vocab size. And on the basis of these parameters, using this embedding layer, you will be able to get a featurized representation. And you will be able to convert this thing into a dense matrix, and then lower dimensions. So that's the main agenda. So let's try to understand. So I have imported one hot encoding because anytime whenever we try to create a new word to vector, first we'll doing one hot encoding. Using the one hot encoding, then I will be able to, using the embedding layer, I will be able to convert them into the newer dimensions. Okay. So let's understand. For the corpus of the data, I have taken this kind of vocabulary: a glass of milk, glass of juice, cup of tea. I am good boy. I am a good developer. And trying to understand the meaning of words. Your videos are good, right? And this kind of sentences I have taken and trying to show you using this kind of list. Okay. So once I get this list, next thing I told you that always we have to mention the what will be the vocab size. Once you mention the vocab size by using one hot encoding, it will be able to convert all these sentences into some sort of indexings. Okay, some sort of indexing, it will be converted. Then the word B, glass, milk, and juice, they will be getting the respective indexes for them, unique indexes, and then it will be try to show you in the 10,000 dimensions. Okay, so that's the pretty simple thing we are doing in the beginning. Once I am able to understand what is my vocab size, next thing is, like I told you, one hot encoding, and then I'm trying to pass the words. Okay, vocab size and words for words in sentences. Okay, and then it will be able to convert. Right, this is the encoding which is given us by this. Means the word is using glass word, using a representation of this kind of indexes. Right, if you see the word is shown by 6654. Again, the glass of milk. Okay, the glass is shown by 998. And if you see again the second sentence, the glass of juice, again you will find the two similar words, that is 6654, that is the, and the glass is 998. Then off is also similar, 8966. Okay, 8966. That's how. Okay, so we can relate here. Once I do this thing, then the main task will be to import the embedding layer. Okay, for importing the embedding layer, what I have to do is, from Keras layers, import the embedding, and then also from Keras process.sequential, I have to use pad sequencing. Now I will try to tell you what is pad sequencing and why require it. Okay, let's wait for some time. And also, whenever we try to build a model in Keras, right? In Keras, whenever I am trying to build any model, we are always using this kind of function called as sequential, right? Sequential function. Let it be a NN, right? Let it be NN, let it be a CNN, or let it be anything, any kind of representation using the neural network. We are using this sequential, and then using this sequential, we are adding the layers. Sequential dot add. Let it be a dense layer, or let it be a convolution layer, let it be a pooling layer, or let it be any recurrent neural network, or let it be LSTM. Okay, so we are using the base architecture same, and that's why we require this sequential function. Okay, once I understand the sequential function, everyone knows about NumPy. And then first thing, try understand that. First thing, I have to tell that what is the sentence length I am looking for. Okay, so whatever sentences I am trying to pass over here, they are having variable length. Okay, so they are having variable length. And in order to perform the word embedding, what I have to do is, I have to bring them to the same length. Just to bring them to the same length, I have to use the concept called as padding, which you guys might be already aware. In convolution, we are also using the padding. By using the padding, we are able to retain the original dimension even when we apply the filters on it. So the resultant matrix will still be remaining and will not be using the significant information, okay, out of this entire image. So the similar concept we are trying to implement over here. And for that purpose, what we need is, we need a kind of a padding sequence. Okay, kind of a padding. So first thing I gave you about the vocab length. Once I understand the vocab length, then I am using one hot encoding. Once I do a one hot encoding, then the next step is using the embedding layer. And using the embedding layer, even to make the sentences of the fixed length, because the sentence length is varying. So I need to convert them using the vectorization, vectorized form. And then for that purpose, try to understand that whenever I am talking about the padding sequence, I have to tell that what kind of representation I am using, then what kind of padding I am using, and what will be the maximum length of the sentences. So maximum length of the sentence is, like we have mentioned here, 8. Okay, so one hot encoding representation, everyone know we have done this one hot encoding, and using which we are able to convert this text to numbers, right? Text to this kind of numbers. This is the glass, and this is the other things. Okay, and then what we have to do is try to understand what this padding is doing. So I told you, if you look at the sentences over here, the first sentence contains only 4 words. Second one also contains 4, then third one also 4, but some others are having variable length like this one. Just to bring them to the same scale, what I am trying to do is, I am trying to add a padding. Okay, what padding will do is, it will just try to create the 0 values. Now I am using padding as pre. You can use padding as post as well. What will be the difference in padding pre and post is, whenever I am using the padding, okay, whenever I am using this padding and when I am trying to, let's look at this example, guys. The glass of milk, these 665499889966 and 11609. Okay, these are four words which are taken over here, last four words, and then since my maximum length is 8, I are still remaining with the four values, right, which I need to give. For that purpose, this padding will help, and this is a pre-padding, means pre towards before even the beginning of the sentence, it is trying to add the zeros. So by adding these zeros, I am able to make a consistency in the all the sentences to bring them to the same scale of the length. Okay, so that is called as pre-padding. Even you can use a post-padding where they will be adding zeros after once the sentence is completed. In this case, this will be like this one. And this is how they will be able to achieve the max length. Okay. Yeah, guys, I told you post-padding. This is how the post-padding will work. Okay. So that these are the three parameters. Once we understand, then see, we have converted that called as embedding doc, where you will to add the zeros, pre zeros, okay, towards this beginning of the sentences. Okay. So let's go back to next thing. Now the thing comes in as like my original dimension are 10,000 vocab size, whatever vocab size I'm telling. Now I have to bring them to 10 dimension. Okay. So for that reason, I am trying to mention the dimension over here. Then once I mention the dimension, I am having all the entire information. What is my vocab size? That is 10,000. Then input size, that is equal to maximum length. Then I am having my one hot representation. Then I have my all the embedded docs. Okay. So let's call the model equal to sequential. Then model dot add embedding. Okay. Rather than using dense, convolution, or RN, we are using embedding. And then I'm trying to pass my vocab size. What is the new dimension I'm looking for? And then input length, which is equal to sentence length. Then obviously we will be using some sort of optimizer like gradient descent. Similar, we are using adaptive motion, adaptive motion with moments, right? Adaptive motion with the moments, something called as with moment. We can have also called as SGD, stochastic gradient descent with momentum. Sorry, okay, with momentum. It is like with momentum, adaptive. Sorry, I forgot the entire word, but it is something called as with momentum. Okay, with momentum. That's what it says, right? We are trying to consider the momentum along with this kind of optimizer. So we are using Adam. Adam always performs best when we are trying to talk about the different kind of optimizers, because it is trying to consider the momentum. And since we are dealing with the sequential data, so the momentum is very important because we are trying to refer towards the time at t-1 as well as the time at t and the time. Okay, you want me to please explain the embedding again? Okay, in the code. Okay, guys, I will try to tell you the embedding. Let's wait. Okay, so it's a very simple thing. Try to understand what is embedding. Okay, what I am trying to do is simply first step. I have this kind of sentence. Okay, I understand. I have these sentences. I have to convert them to numericals. Okay, to numericals, and that job will be done by one hot encoding. One hot encoding. What this one hot encoding does is, and then I'm trying to give us the entire length, that what kind of length I'm looking for. Here let's suppose I'm trying to tell you that 10,000. Okay, and 10,000 vocab size. This is the vocab size I'm trying to give. Then what it will do is it will try to convert all these words into the indexes. Okay, like a number. They will try to assign a number starting from 0 to 9,999. Okay. So the index is starting from 0, right? And that way. So for each and every word, there will be unique number assigned. That's what the one hot encoding will do. And this is what I've done, right? And whenever it is trying to represent any data, let's say the glass, okay? The glass is 6654. 6654. So this is the index for the glass. Then how it will be represented starting with 0 to till 10,000. It will try to give you all the zeros except here it will try to show you 1. and again all the zeros. This is how it will try to represent whenever I am calling this kind of vector for the D. Okay, for the glass it is 998. That's how it is converted, guys. This is what the one hot representation is doing. Once I am able to do this kind of one hot representation, right, I am able to convert them into the numbers. I have assigned a unique number for each and every word. Okay, in the range of 10,000, 0 to 10,000. Then the next thing what I have to do is, whatever sentences I am having, right, whatever sentences I'm having, these sentences are having variable length, right, variable length. They are not same length sentences. Always the sentences whatever I am giving to my models or my deep learning machine algorithm or neural networks, the sentences won't be same always, right? As a human being, even as a human being, you will never be able to speak same sentences, same length sentences, right? Some sentences will be very short, some will be very lengthy, but just to bring them to the consistency, what is the max length possible in the Keras? Guys, you can give any length. It is as per your use case, okay? As per your use case. So next thing will be to bring them to same consistency. That's why I'm using max sentence length. And by using the max sentence length, we are trying to bring them to the same level. Now, instead of only having 4 words, I am trying to bring them to the 8 words. That's how it will be done. And then I am calling a model, and within the model, I am trying to pass a vocab size that is 10,000. Then whatever dimension I am trying to achieve. Previously, I gave 10,000 dimension. Now I want it to be represented using a 10 dimension only. Then input size equal to sentence length, that is 8. That's how then I am trying to compile with the optimizer and the mean square error. This is the accuracy I am trying to check for. Mean square error. Then I will try to print my model. Okay. Adaptive moment estimation algorithm. Correct, guys. Thanks for the name. Adaptive moment estimation with the adaptive moment estimation. Yeah, with the time. Yeah, that's the ADAM thing. Okay, that's the ADAM algorithm. And this is not the only algorithm with the momentum. There are other algorithm also, which gives you the momentum, which is called as our normal stochastic gradient descent with moments. Okay, with moments. This is also there. Then RMS prop is there. RMS prop, ADA delta is there. ADA grade is there. There are various algorithms, but out of that, ADAM performs very best. It has been proved and it has been tested that ADAMS gives us a best result. That's why we are trying, and since we are working with the sequential data, so that's why I'm trying to take a ADAM over here. Okay, and then we'll try to print our model. Let's go back and understand very quickly. Then I'm trying to print my model, and this is how the model will look like. Embedding using size 0 to 9. Guys, embedding is a layer, right? See this one. This is the layer I am trying to import. Okay, embedding is already defined over here. Keras stands for import embedding, then sequential, and then pad sequence. Okay, so it is already mentioned. So embedding. Okay, embedding. This is how the embedding looks like. Then the output shape will be like 8, 10, maximum length 8, and then total sentence 10. And these are the 10,000 parameters. Okay, and this is how the model dot predict. Now comes the question that when I have converted them, try to understand that whatever their sentences were there, whatever the length was there, okay, one word is now shown in using the 10 numbers. Okay, so try imagine 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. Now it is able to show you using the 10. Okay, understand? Now try to understand how it will look like. Okay, so this is my first sentence. What was my first sentence? The glass of milk, right? And then I converted them using into the fixed length of 8. So for that purpose, it is showing 8. Now, how these 8 words will got converted into 10 for each and every word, there will be a 10 dimension representation. Try to understand how. So this is how. This is for 0. Again, you will see that this one and this one is same. Why? Because we have 4 zeros. For that, there is a same representation. First 4. Okay. And then we'll be having like 665, which is again different. This 65 is the glass of milk. Okay. That's how using the 10 dimension, it is able to give us the feedback or show us the numericals. Okay. Understood, guys? Pretty simple, I guess. All right. Just give me a confirmation. I can go ahead and now and stop sharing the screen, and we'll switch back to our presentation where I will be using LSTM, and we will start with the LSTM neural network, guys. If anything is there, yeah. Okay. Okay, guys. Just give me a confirmation so I can go back now. If there are no further questions, yeah, okay. By adding padding, we are adding zeros. Correct, guys? Yes. By adding padding, we are adding zeros. Why we are adding zeros? Because we need to bring them to the same level, same length, right? By using same length, I'm trying to achieve then without changing the meaning. I can even add zeros, or you can add padding as one or something like that. This we already seen in convolution neural network. Okay, all right. I hope that that's it. Then let's go back. We have to discuss many things, guys, today. All right. Okay, so now we'll switch to LSTM to try to understand, guys. You have to also see this kind of implementation of sequence using LSTM. Okay, many things need to be discussed. Before that, let's go back to LSTM and try and understand. Very interesting topic. Very interesting topic, guys. Try to understand what is LSTM. Yeah, guys, RNN is not over. RNN, this is, we have just seen, guys. Try and understand that what I'm trying to tell you. RNN architecture is base. Okay, base. We can call it as a vanilla flavor. Vanilla. Okay. On top of this vanilla, we are having different variants. Okay, variants. These different variants we're trying to understand now. So guys, all whatever implementation we'll be seeing are this is for RNN only. Okay, I had to understand. This is RNN implementation only, but with the different flavors rather than vanilla flavor. We're trying to understand the LSTM, how the LSTM is working, what is GRU is working, what is sequence to sequence architecture. All this architecture we'll try to understand. If I try to discuss all these things, we'll not have enough time. That's the reason. All right, guys. So let's start with the LSTM. Very important topic, crucial topic for the day, guys, and very interesting. Okay. What is LSTM? Why we require LSTM? All these things we'll be going to speak here. And this is very popular, LSTM. Very popular neural network of the RNN, okay, of the RNN family. So try and understand what is what is recurrent neural network, what is called as LSTM. Okay, when I try to understand LSTM, okay, so first we need to understand that what is the problem with the long-term dependency, where there is a shortfall in the recurrent simple neural network, that is simple RNN. Simple RNN, or you can call it as naive RNN. Naive. People call it as naive or vanilla RNN. Vanilla RNN. Okay. Whatever we discussed today was vanilla RNN. Now we need to understand that what are the issues with the vanilla RNN and or naive RNN, and how we can tackle this naive thing of this RNN, and that we have to understand in terms of the long-term dependencies. Okay. Yes, guys, gradient problem, vanishing gradient problem, all these problems will be solved. And in order to deal with this kind of things, they have given birth to a new neural network, which is called as LSTM. Okay, let's try and understand first what was the issue and what is the problem, and how this long-term dependency is not able to be handled by the simple RNNs. Okay, let's imagine that you are trying to understand or trying to carry out the task which require the information about the recent past. Okay, recent information. Let's imagine you are trying to create a model which predict the next words. Okay, so if I am saying that the cloud are in, and then what will be the next word? Obviously the sky, right? Because I can understand using this kind of information, the clouds are always in the sky, right? This I can relate. There is not long gap, right? There is no long-term dependency in the word. So the gap is relevant information, and the place that is needed is small, right? The gap is small. Gap in terms of not word, guys, not a length. Okay, I understand. I'm not saying that I'm trying to predict one word. This is not the thing I'm trying to convey here. So what I'm trying to convey is when I am having a 75% of information with me, just to predict the next 25% of information, I will not require that kind of a logic, hard logic, right? I will be able to convey it, or I will be able to guess it, right? So, but when I am trying to speak about the some complex sentences, right? Complex sentences like I grew up in France and I speak fluent. So could be options. Now I need to understand the entity over here, entity, intentions, intention, and the relationship with t minus 1. If I am talking about time t, I need to understand what is the relationship with t minus 1 and what all the information I am able to collect and what is the chain of the thoughts here, chain of thoughts. Okay, chain of the thoughts that I need to understand. And in order to guess that it is a French, or maybe if you guys know about the France, okay, about the France, in the France region, in the Alps region, okay, in the Alps region of the France, there are many people, okay, there are many people who even speak German, even speak the German, okay. There's a huge community which lies and which speaks the German, and there are also people who speak Spanish, okay, very few people. So it is not that only people who stays or who is grew up in the France will be able to speak French, okay. There will be also people who lived in the Alps, okay, Alps, they will be able to understand the French as well as the German language, okay. So that is the beauty of this language, or that is the beauty of the guessing of this word, that the French requires, okay, the next friend, next word, French requires understanding of entity and also the thoughts and also the context. So I grew up. This is the context that I lived there. I lived there, right? I grew there, I lived there, and then I grown up over there, and that's how I can understand or speak fluent French. Okay. So this kind of consistency, whenever we are talking about, the gap is very huge, right? The gap is huge about the information where it is needed, it is become very large. And unfortunately, these kind of gaps are not filled by the RNNs, simple RNN or naive RNNs. So what it requires, how we can solve this problem is, we need to save this information. I grew and France. I grew and France. This information need to be stored somewhere in the cell, right? Even for the human being, whenever we are trying to understand or having a conversation, we are trying to store some information, right? And on the basis of that information, now we are performing our dialect, right? Dialect or our speech. That's how we are going further, right? So for that purpose, we need something called as storage or cell, which will be able to remember something, which will be able to remember something. And that is how it gave a birth to LSTM. LSTM, okay? So try and understand what is LSTM. LSTM is nothing but a recurrent neural network with a memory, okay? With a memory. So that's what I am trying to show you. Recurrent neural network with a memory. So vanilla RNN operates in multiplicative way, okay? Repeated tonnage. And then due to which we were not able to understand or have any kind of memory. In order to solve that, they proposed two neural networks or two flavors, which is called as gated GRU and gated recurrent neural network, and one is long short-term memory, okay? Long short-term memory. Now these are the networks with the memory where we'll be able to store some information, we'll be able to have some context to the sentence, and this is how the LSTM looks like, and this is how the GRU looks like, and this is called as the gates. This is called as a memory cell. Let me clarify this thing. This state is called as a memory cell, and then we'll be having one gate here, which is called as forget gate. Then there will be a input gate, and there will be a output gate. Okay, this is how the part of that we'll try to understand. Don't worry, try to understand, go in detail that what is recurrent, what is LSTM, what are different parts, how is the memory playing role, what kind of operation are happening. And then we are having also GRU, gated recurrent neural network, which looks somewhat different from the above one. That what it trying to do is trying to combine the forget gate and input gate with one gate, which is called as, let's say, alternate state, current state, and hidden state. That kind of states are there, okay? And then trying to modify the things, and what could be the advantage that I will try to able to discuss you when I'm trying to go to this GRU cell, okay? GRU cell. So I think the I was able to set a context pretty much very well, that what is LSTM, why it got a birth to this LSTM, what is the issue with the vanilla neural network. So try and understand all these things, entire LSTM network one by one. Very beautiful concept, guys. try to understand. And this is the diagram where you will be able to see that in recurrent neural network, this is like, let's say, output t minus 1. We are giving output, we are also giving input, and there are weights associated with it, and then it is passed through the sigmoid function, and it is able to give us the output, right? Output. This is what happening. We seen yesterday. Whatever information, whatever output is there, that consists of the weights, and then also output h t minus 1. Okay, tan h function not sigmoid. Yeah, guys, tan h function not sigmoid. Okay, so let it be anything. They will be using sigmoid, so I will try to show you. See here, they are using sigmoid as well as tan h. Both the function are used here. This notation denotes the sigmoid. Okay, and then they will be using tan h. Okay, but in recurrent neural network they are using tan h. Okay, so let's understand. Okay, let's understand that what they're trying to do over here. So this is how it is happening whenever we are trying to perform any application on y hat. Our output consists of the function. Okay, this function consists of the weights. Okay, weights, and then multiplied by the output, which is output of t minus 1, and the current input at t, right, plus biases. This is how it will look like, right? This is what the operation is happening. And then here, what we're trying to do is, we're trying to have this kind of a memory cell where we will be able to save the, in this cell, we will be able to save some info. Save some info, which is having pertaining to the previous state. Then we are passing the input. We are passing the input, and the passing the input will also try to understand whether we need to forgot the previous information, or not, or whether we need to carry that information. Once we carry that information, then here it input gate, we are giving additional info. We're giving additional info, and then basis of this, we will be able to generate the output. That is what is happening. I know it looks somewhat complex, but don't worry. I will go to entire all the things. I will try to understand each and everything one by one. Okay, before we try to go into this LSTM, guys, I want you guys to understand some kind of notations. Okay, what are the notations? Whenever now you see this kind of a rectangle box, it is called as neural network layer. Okay, this is a neural network layer. Then whenever we're talking about this kind of a circle, right, here there is a circle, here there is a circle, here is a circle, that is called as point-wise operation. Means either we are multiplying the information or we are adding the information at that time. Okay, that is called as point-wise operation. These square rectangle boxes, yellow boxes are the layers. Okay, these are the neural network layers. For that case, it is a RNN layers. Okay, RNN layers, and then these arrows are nothing but the vector transform. Means we are passing the information, right? We are passing the vectors of the information, vector of the information. That is what we are passing. And when I am trying to show you like this one, when the information is coming at this time, right? We are trying to combine the information, right? This is called as concatenation. Okay, we are giving a information of the previous output, and we are giving a new output, right? This xt, and this is x, or output t minus 1. So we are trying to concatenate, because that is what is happening, concatenation, and this is copy. Okay, whenever we're trying to say this kind of arrows out of this one, we're trying to copy it. Okay, so try and understand. This will help us to understand the things. And this is a sigmoid layer. Okay, this is a sigmoid layer which is passing the output into 0 to 1, and then after that, if you see, this is the pointer operation which shows the multiplication. The pink X gate is a pointwise multiplication. That's what we understood. Circles, pointwise application. Normal arrows, vectors, that means numbers or words which are converted into numbers that are passed. This means we are trying to join, and this means we are trying to copy. Okay, clear everyone? What are the notations? And this is sigmoid, right? This is called as sigmoid. Whenever there is a tan h, they will show you tan h. All right, guys. So let's deep dive. I told you there are 4 parts. Guys, that will try to understand where the copy is used. Okay, I will tell you. Don't worry. So before we jump into the LSTM, guys, try to understand there are 4 parts to LSTM. What are 4 parts? First is cell state. Then second is forget gate. Then third is input gate, and fourth is output gate. Fourth is output gate. So whenever we try to understand, guys, this is very beautiful concept again, and there are very much blocks dedicated around this LSTM, right? Whenever we are people are trying to understand the transformer, right? Transformer, sequence to sequence architecture, transform or bidirectional RNNs, right? BERT is nothing but bidirectional RNN encoding representation for the transformer BERT, right? Or GPT is kind of a pre-trained generative transformer, right? Pre-trained generative transformer, GPT, pre-trained transformer, right? Generative pre-trained transformer, all this kind of architecture, right? All this kind of architecture, whenever you're trying to understand, or let's say for that reason, even you are trying to understand the topic modeling, or let it be any transformer model. These are the transformers are the base, guys, for the large language models. Okay, all these transformer also consist of the encoder and decoder, and this encoder decoder in fact consists of the LSTM and the RNN neural network. Okay, this kind of feeling, and all these operations are happening there with the complex way. So I will try to tell you one by one. So try understand. I told you there are 4 states. One is memory, second one is forget gate, third one is input, and fourth one is output. Okay, so try understand what is this, and this combines the entire LSTM cell. Okay, that's what the operations are happening. Let's go to these things one by one. These things I already told you guys that these are the operations which are happening over here: input gate, forget gate, output gate, and the cell state. Okay, so try to understand what is the cell state first. Okay, this is called as cell state, and what is the cell state and what a kind of operation it is doing. Okay, all these things we'll try to understand now. Okay, so first thing, cell state. Okay, what or cell state is also called as memory cell. Let me call it as memory cell. Okay, this is what the memory cell is, guys. This entire operation, which is this point towards operation, then there is a vectorized information which is flowing through. Okay, this entire part is called as memory cell or cell state. And what it does, okay, what it does, whether it is stores the information, okay, it's try to store the information. There are 2 things which is done: remember and forget. Remember and forget the input. That's what it does. And it performs the pointers operation. For that, one operation you see multiplication, one operation addition. Okay, I will try to show you what this does and what are these operations. Okay, let's consider that I told you that this memory cell either remember or forget the information. Okay, remember or forget the information. I'll try to write it here. The main intention is to remember or forget the info. Okay, and how does it perform that kind of operation? How do we remember? How do we remember now? Okay, that's the main question. How do we remember? Now we have to remember based on the context. Okay, based on the context. Based on the context, we have to remember or forget the things. Now you will again ask, what do you mean by context? Okay, so try and understand what do you mean by context. Now, let's imagine that you are working on a topic of generating the text. Okay, generating the text. That's my main aim. Okay, so I have to generate the text, and for that reason, what I'm trying to tell you is, let's say I'm saying that my name is Vikas. My name is Vikas, and then next thing I'm trying to tell you is my age is 35, and then I'm trying to tell you some other information, that I am from Pune. This is how I'm trying to tell you, and then what we're trying to do is we're trying to generate the text. Okay, if I give you this information, obviously next thing what you understand is a recurrent neural network or a cell information is that maybe now you will try to tell that I speak fluent Marathi. Okay, Since I am from Pune, I speak fluent Marathi, or I can also say that along with Marathi, I can understand Kannada, I can understand English, I can understand Hindi, and I can understand little bit of Telugu. Okay, that's what I understand. Yeah, guys. So, okay, so this is what I'm trying to tell you. But let's imagine that whenever I are generating the text, okay, that main input is that to generate the text. But if all of a sudden now context is going very well at that time, when I am saying I am from Pune, I am this age old, and then I can speak this kind of language. But if all of a sudden if says I am Vikas, then I am Vikas, and then my sister name is Maya. So all of a sudden, what I'm trying to do is, rather than giving an introduction, I'm trying to change the things. I'm saying Maya. Now what happened is, Vikas is entity, is a noun. Then I am trying to tell you that I am from Pune. So I am trying to tell you the place. Again, it is an entity, geographical location. Now I am trying to tell about my sister. Okay, sister. The context is changed. Context, it changed, right? So whenever there is a change in the context, what happening is new context is coming into picture. That is sister. Now, till now, I am talking about Vikas. Now, I am trying to change the context. I am trying to talk about my sister, right? So, at that time, what I have to do is, here, in memory cell, what I have to do is, I have to change the context. Once I change the context, I have to forget something, right? I have to forget something, and I have to add new thing. What new thing I'll be adding? That there is a sister also, and her name is, like, say, Maya. So, that thing I have to add, and I have to forget some of the information, okay? But still I will be retaining some information. I will am not completely forgetting what is Vikas. Okay, but because I am talking about the Vikas, and now I introduce a new context. Okay, so this is what is called as change in the context. Whenever there is a change in the context, I have to remember or forget the information, and whatever that information is there, that is performed using the pointers operations. Okay, with either multiplication or addition. That is what the pointers operation says. Now try to understand what is pointers operation. Pointers operation means what? Let's say I am trying to denote this pointers of operation multiplication. Will try to understand what do you mean by multiplication now, and what we're trying to achieve using this multiplication operation. Let's say I'm trying to denote any word. Let's say using 1, 2, 3, 4, 5, 6, this kind of embedding. And now I'm trying to tell you that there is a something there. Let's say there will be either we have to forget, we have to do two tasks. One we have to forget, or we have to remember, right? That's why the memory cells are there, and based on the context, right? Based on the, I will try to write somewhere here. Based on the context, we are trying to add or change something or fill the information. So let's say I am trying to represent anything using 1, 2, 3, 4, 5, 6. Okay, this is my vector. And then whenever I try to multiply the things, let's say I am trying to multiply this by this kind of vector. Let's say this is 1, 2, 3, 4, 5, and 6. And then I'm trying to multiply by 1, 1, 1, and then 0, 0, 0. That means what? Whatever words I am trying to show here, some of the words will remain same. Like a resultant vector will be like 1, 2, 3, and there will be 0, 0. That means what? I am trying to forget something. Whatever 3, 4, 5, 6 is there, I am trying to discard that information, okay? And I am trying to retain some information, that is 1, 2, 3. That's why my resultant cell will look like, or resultant dimension or vector will look like, right? Means what? What I have done, I have forgotten some information of 4, 5, 6, and I have retained some information. That is what the multiplication is doing. Understood, guys? And then there is the operation called as addition. Okay. In addition, also what I'm trying to do is, whenever there is a change in context, I told you, whenever the context is changed. Let's say I was talking about Vikas, and I'm from Pune. I'm talking about I can speak fluent Marathi. Then all of a sudden, I am trying to add my sister. Okay. So the context is changing. So that will be added. Like, let's say, how much percent should you forget and remember? Guys, it depends. Okay. It depends, and it will be done by the recurrent neural network and the LSTM, because we will be doing a training line by line, and on the basis of this on the basis of this forget and this sigmoid, and the basis of this tanh function, they'll try to understand if there is any meaningful information. If there is any meaningful info, they will try to retain. Otherwise, they will try to forget. That I will come to know, guys. You'll come to know when I'm talking about the input, get, hidden state, and all other things. wait for some time, and then you will be able to understand. Okay, so we are talking about the memory cell. We're talking about the memory cell. Okay, the cell state, and in this cell state, it is add or remove the information, or forget or remember the information. Now I told you it does that on the basis of the context. Whenever there is a change in the context, there is a change in the context, it will be able to add or remember, or it will be able to forget some information. And this is how the pointwise operation look like. I told you, whenever we trying to perform the multiplication, and if I am trying to show something by 1 2 3 4 5 6, and if I am trying to multiply by 1 1 1 0 0 0, then I will be getting this kind of resultant state. 0 0 0. That means I am trying to remember something and trying to forget something. That's what is happening. And when I am trying to add something, whenever I am trying to induce my sister, I am change. There is a change in the context. When the context is changed, and in addition, also I have to bring some information. The similar way, I have to make a plus addition. Let's say 1 2 3, and this time 4 5 6. Okay, 4 5 6. Just a simple representation, guys, so you don't have to get confused. That's why I'm trying to tell you. And then whenever I trying to do information, right, I'm then trying to do information addition operation. At that time, what I will try to do is, if there is a change in context, I'll try to do this way: -1 -1 -1, and then this is 0 0 0. That means my resultant vector will be like this one: 0 then 4 5 6. That means I am trying to add this 4 5 6, right? I am trying to remove 1 2 and 3. Okay, just hypothetical example I am giving. Don't go by mathematical calculation. This is how the pointers operation plus will be working. Like this plus information, it will be able to get a new context information, add that new context information, as well as multiplication operation will also try to understand what to retain, what not to retain. Okay, this is what the entire cell state is doing, and that is what the entire things are done. And these things, since we did not have the privilege in vanilla flavor, we did not have, or in naive RNN, we did not have this kind of a privilege of storing the information. Now it is doing what addition does. Guys, addition does, I told you, when there is a change in the context, it try to add the information. Okay, how it adds the information on the basis of the input, that I will try to tell you in the next step. Okay, I guess now the cell state is clear for everyone. And what the cell state, guys, this is very important information. So sometimes whenever people try to understand this kind of context, right, this kind of context, and most of the times people fail to understand LSTM, fail to understand, and by looking at this kind of examples only, or this kind of complex diagram, people give up. Okay, so it is better try to understand and give all your attention, right? Once you understand this concept for next 5 minutes, it will be very easier for you guys to understand what is happening and what are the implementation for it. Okay, so let's try to concentrate. Now we understood what is the cell state. Now understand what is the input gate. Okay, we understood all this operation, what is happening in the addition state, what is happening in the multiplication state, right? Let's try to understand what happens in next in the forget gate, and how the forget gate will look like. This is entire thing is called as memory cell. Okay, cell state. Out of this one, now we have discussed this part only out of entire LSTM. Now we need to understand this part, and this part. That is forget gate, input, and the output. And this is how the entire LSTM will be consisting of. Okay, so let's move to next thing, that is forget gate. Don't get confused about this notation and everything. I will try to teach you what is happening and what is not happening. This just for the information. Once we understand all these things, then you will be able to understand what is the output consist of, what is the forget gate consist of, what is the input gate consist of. Even though it is looking complex, guys, the main idea or ideology behind the same thing is same. Even you go to anything, let's say in sigmoid also, we are passing the sigmoid function forget gate. What we are trying to pass? The weights, right? This weights, this is input, this is input and output of t minus 1, and this input is of t. Okay, and this is bias. This is bias we are trying to add, right? And this is all these things are passed to the sigmoid. All these things are passed to the sigmoid, and we are having weights. What kind of weights? I told you, right? In neural network, whenever we are trying to pass this x, this kind of things is there, right? with respect to t, there will be one weight over here, and there will be one weight which will be given W dash along with this output, right, of t minus 1. So this kind of things is happening. So that's why we are having two weights. Let me show you with two colors. Two kinds of weights are there, and one is output of previous one and input of previous one, and it is getting concatenated, right? That is what we've seen, and we're doing a multiplication operation over here. That's why you can see multiplication over here, right? And plus we are trying to add the biases. That's it. Weights and biases. How this look like? Y equal to mx plus c, right? Weights and biases. That's what. Okay. Try to understand the entire ideology or complexity what lies behind, and then you will not ever get confused. Okay, about these things. The things will be remaining same. Only the few more mechanism has been added, called as memory cell, forget gate, input gate, and output gate, and then the memory of retaining some information and adding some information along with it. Okay, based on the context. So let's move to next thing and try to understand what is forget gate. First step is like we understood memory. Once we understand the memory, then what we have to do is we have to decide. Okay, when we try to generate this kind of sentences, we have to decide that what information has to be thrown away from the stale state, right? Memory. We understood the memory, and in second operation, whenever I passed one sentence, okay, when I passed one sentence, and in the next sentence, what I have to do is I have to remember something from the first sentence, and I have to process the second sentence as well. I have to concatenate the things, and what kind of things I have to remember is based on the context. Based on the context, if the context changes, I have to remember few context things, and I have to add the information. That is what is happening. And the forget gates help us. What is forget gate works? It helps us to throw away some information from the self state or from the memory. Okay, that is what. And this is how the forget gate look like. Okay, try to understand what is the forget gate and what it will do. Again, I will try to also explain you the things. Okay, what is happening over here. So in forget gate, what is happening is we are trying to perform some kind of operation. Like in forget gate, what we're trying to do, this is the forget gate. Okay, so now we are trying to pass some information from the previous state and the current input and the previous output, and this is passed, and along with the weights. Okay, there are weights W dash and W, and this is passed to the sigmoid function. Now what sigmoid function is doing, whenever I am trying to pass these weights into the output h, that is h t minus 1 into x t, right? This I am trying to pass, and this is some kind of bias. Okay, so a constant number, it is constant number, some sort of constant number. This I am trying to pass between the sigmoid function. On basis of the sigmoid function, okay, on the basis of the sigmoid function, on basis of the context, okay, it will be able to understand and able to give me a representation between value between 0 to 1. If that information is not critical or there is a no change in the context, what it will do? It will try to, if there is no change in the context, then the resultant value will be into the zeros. Okay. Oh, sorry. When there is no change in the context, then resultant values, there will be more ones. And then when there is a change, that will be zeros. Okay. If I apply multiply anything with the zeros, obviously it will become 0, right? And if I multiply anything with the 1, it will remain the same, right? Whatever information is there, it will remain the same. That's the logic. Okay. That's the logic they are trying to perform over here. Okay. Let me clarify. This is what they are doing. Okay. In forget state ft, they are trying to pass this information. Okay. In the basis of this previous output, current input, along with the different two weights, W dash and W weights. Okay. And this combination is a multiplication. And then they're trying to pass it to the sigma in order to understand whether I need to calculate or carry out this information, or whether I need to discard this information. Okay, that is what they're trying to do. Now try to understand that what is happening and what is the real-time example, how these things are happening in the forget gate. Let's say that in previous state, if there is a change in the context, okay, there is a change in the context. Let's say whatever output is there, ht, then whatever output I am trying to pass, input I am trying to pass, and in the basis of that, I will be able to get a new output, that is ht1. This ht and ht1 will be same if there is a no change in information, no change in info, that it will remain same. If there is a change in the information, that means there is a change in the context, then HT and HT minus 1 will be different, but this entire HT will not be discarded. Some of the information which is required will be taken into consideration. That's why we are trying to give a probability with kind of 0 to 1. If I'm trying to pass something like this one, 0.5 or 0.4, some of the information will be retained and all of the information will be not lost. And if I'm trying to say 1, that means there is a no change. It is same. Okay. That's what happening. Try to understand this way. If the previous information which I gave, okay, the vectors, let's say vector of the king and the vector of the queen, whenever I'm trying to compare this kind of information, mostly whatever the representation is there, okay, mostly it will be looking same. Mostly it will be looking same. Okay. If I try to take a multiplication out of it, whatever resultant factor is there, it will same. If I'm trying to pass this information as a 1, 1, 1 in this, okay, and this sigma will be able to give me 1. That means there is a no change in information because king and queen already they are from the royal family. They are royal family. Maybe their genders are different, but they are belongs to humans. They are royal family. They are humans, and then they also have an age, and they also try to perform some sort of information like they will be having liking in the food. And if I have a more like more kind of features, let's say or you can speech. So this kind of features is there, then whatever information I will be getting like will be once because they are present in those feature categories, right? For that purpose, whenever I try to compare king and queen, okay, there will not be much difference. But whenever I am trying to compare king vector along with the poor vector, okay, poor person vector, that will be the word embedding will be different and the context will be different. At that time, it will try to forget the information, right? At that time, it will be not more ones. It will be 0, 0, zeros and only 1 will be 1. Why 1 will be 1? Because both are humans. Both are humans and some kind of things will be like 0.2 because they have age also, but mostly they don't belong to royal family. Royal family, they don't belong to royal family, or maybe their likings are different. Okay, this kind of characteristic. Okay, at that time, this will be able to perform the matrix multiplication, which will be able to give you like whether you need to multiply by 1, 1, 1 or whether you need to multiply by 0, 0, 0 or 1, something like that. Okay, whenever there is a change in the context, there will be 0, 0, zeros and 1. So it will be trying to show you that there is a different thing. And there, if there is a dense matrix which is giving you ones, that means there is no change in information. So no change in information is try to retain the same thing. And there is a change in the information, then forget something and add something. Okay, that's what the entire forget cell is doing. Okay, this is how the operations are performed, and that's why we are using sigmoid along with it, right? And the same things is happening. Okay, weights, inputs, biases, and everything. So this is what is written. Whenever model observes a new subject, it want to forget the old one from the memory. Okay, and try not forget completely, but forget some of the information. So now we are clear with what is memory state, what is forget gate. Now comes to next part is called as input gate. Try to understand what is the input gate and how it is trying to perform the things. Okay. Now input gate consists of, this is how the input gate will be. Okay. This is what the input gate will be. Now first what we have to do in the input gate is, I told you that whenever I am trying to tell you that I am Vikas. I am Vikas and I am from Pune. Then I speak Marathi. This was okay. Then I also give you additional information about the speech that I can understand Kannada, I can a little bit understand Telugu, I can speak fluent English, I can understand Hindi as well, right? So this additional information I am trying to give you, right? So I need to add this information. So this is the additional inputs I am giving, and along with it I have a previous information that I am a Vikas and my age is something like this, and I am from Pune, geographical location. All this information is there, and the next sentence is giving me additional information. So what I will try to do is, there is no change in context, right? Till now I am just talking about myself. There is no change in context. So what I have to do is, whatever other things are coming up, that I have to add, right? And if I am trying to talk about my sister, that means there is a new gender has been introduced, that is female. Till now we are talking about the male, there is a new gender has been introduced. So what I have to do is, I have to add this gender information. I have to add this gender information. That is what the input is doing. Okay. So if I talk broadly about what is the input gate is doing, input get will try to give you a additional info to a memory. Okay, so this plus operation, additional info, right? I told you plus operation gives a additional info. So that is the main thing of this input gate. This is the input gate where it lies in the entire cell. This is forget gate. This is input gate, and this is output gate. And this is memory cell. Okay. So what when I am talking about the input gate, I told you the context. If there is a change in the context, what we have to do is, if, let's say they have even taken an example, model want to add the gender of a new subject to the cell state, then replace the old one with the forgetting and then add a new one. Okay, add a new one. So that's what I'm saying, that whenever we are trying to talk about the input gate has to do with the addition of the information. Additional information. Along what additional information in the memory cell? Adding the information in the memory cell. Okay, that's what it does. Try to understand what it does and how it does. Okay. So what we are trying to do is, there are two types of operations which are performed. One is sigmoid operation. First, we're trying to concatenate. This is the concatenation operation. We are taking output of previous one. Next input, we're trying to concatenate it. And then what is the concatenation? That is going through the sigmoid first. Sigmoid will be able to generate between 0 to 1 values. Okay, and all these values again will be combined with the alternative state. Alternative state is like tan h function, and that will be passed through the tan h. Okay, now this information is passed, same information. Okay, same information along with the old output, input, and the bias, along with this weights, both the weights. This is passed with the sigmoid function first, which will be able to give us a 0 to 1 information, and then similar information. Okay, similar information, if you see ht minus 1 xt, and this one also passed with the next weight within the, again the next weight with the tan h function. Tan h will be able to give us information between +1 to -1. Now what they're trying to understand is, whenever I am trying to give an input, okay, whatever input is given, whether that input is significant, or not significant. Okay, that's what they're trying to do using the tan h function. Once I understand whether it is significant, it will be able to give me plus or minus something, and that's how the operations will happen, and it will be able to add the information. Let's take this kind of matrix. This is giving is between 0 to 1. This is giving plus and minus 1. Whatever information I have taken, current information and the previous information, and basis of that information again passed to tan h function, and on the basis of that, it will try to generate two matrices. And on the basis of that matrix, I will try to perform the operation and I will try to understand whether I have to add information or not, or whether there is a change in the context. If the context is changed, add the information. No context is changed, don't add the information. That is what is happening. And that's addition. When there is addition happening in the memory, for that purpose, that input is coming from this input gate. Okay, and input gate, whenever we're trying to give an input to the input gate, at that time also it will try to remember that whether there is a significant change or no significant change. For that purpose, they are passing information in both sigmoid and tan h, and within the sigmoid and tan h, they are trying to generate this kind of vector, and they will be performing kind of operation over here. And on the basis of the operations results, they will be able to understand whether to add or not add. Okay, this is what the entire input is doing. Input gate. Let's try to understand if this sigmoid has created this kind of information, right, between 0 to 1, and this tan h is giving you like this 1 1 1 1, and this 1 1 1, and this is giving you like 1 0 1 1. Then what will be the result? 1 0 1 1, right? So that means some information is lost, but most of the information remains the same, because more of one is generated. More of one is generated means not a significant change. If more of -1 is generated, that means there is change in information, right? There is a change in information. So that's how we're trying to understand. Okay, that's what the addition is done, or whether we don't have to do any addition. That's why they are using two gates. One is alternative state, one is input gate, and they try to combine with sigmoid and tan h, both the things. If you see, both the operations are both the inputs, previous state and inputs and weights and everything same, but they are using the different operations, activation functions. On the basis of this, and then trying to compare these vectors, they will understand what to do. Okay, now we are clear till here. So what is forget, what is now input, and how is the memory getting updated? Okay, That's what they're saying. Want to add anything? Give a input, new input. Like I gave my input to you guys that I am from Pune, from India, and then I'm speaking Marathi. Also, I am giving additional information, like I kind of speak this kind of languages. And my sister, okay, I'm talking about my sister. There is a change in the gender, and then I'm also trying to add this information. Okay, so that's a pretty much information, guys. We can say how much information from input is important, sigmoid, and how much is significant. Yeah, guys, they see that's the same idea, right? That's the same idea that what information has to be retained, what information has to be retained, and what has to be added, concatenated. Okay, that is what is happening in the memory. And this is same thing is passed again. Okay, and this operation is passed again, and then that's what we're trying to do. By using the sigmoid and tanh, they are trying to create this kind of vectors, guys. Try to understand. Tanh is giving something between 1 and -1, 1, 1, -1. And if you want to discard something, obviously we will have to multiply by zeros. And if you want to retain something, you have to multiply by ones. That zeros and ones are created by sigmoids, and then tanh is giving you 1, 1, 1 or -1. So this combination will be able to get you generative the filtering. This combination is giving you filtering. Whenever I am trying to multiply something, it becomes 0. And whenever I am trying to multiply by 1, it is remains the same. Like we understood, king and queen, the same. The king and poor, different. Right? At that time, this kind of encoding is generated. And then on the basis of that, they are trying to filter the information. And that's what is passed to the memory cells to carry out. So once we understand these things, then next part remaining is like output gate. So what should be the output now? What output role is? Now, this is very important, guys. Try to understand what output is doing. Okay. Why are we doing this and what is the need? Okay. Let's understand output gate. Now, the third step. Okay. Third step is output gate, and this is what is happening in the output gate. Okay. Once we are able to finish this part till now, and this whatever information we have added till now, right? Forget gate is helping us to add a forget. Memory is just sparing the information. Then we are adding some new information at xt, and then we are deciding whether this information is significant or not significant. Then that is getting added. Then it comes to next thing, which is called as output gate. And then output gate again, see, understand that whenever we have seen this kind of information, right? This is passing the information, copying the information. We've seen this kind of stuff. This is copy information. This whatever information we have, this is copying. And then whenever you are talking about this thing, it is flowing the information. Okay, flowing the information. So whatever information is there, we are trying to copy that information, and then we try to perform again a pointwise operation over here. Pointwise operation, and the basis of the point of operation, what we're trying to understand, to look at this equation, and then we'll try to understand what is happening in the output gate. And what is the main of the output gate? What is the main thing? Again, out of whatever addition is done, like previously we are carrying some information, some info was carried out at t-1. Then recurrent neural network, how it works, that again I try to combine t-1 and again combine the new input. This combination again passed through the multiplication of the weights, and then it is passed through the sigmoid and the tanh. Then try to understand whether there is a change in context or not, or whether there has to be some addition done or not done. Okay. Then whatever addition is done, again that information is now passed combinedly to the output gate, and output gate will now decide the final output, what has to come out. Okay, what has to come out. So that's why they're trying to first copy the information, this one, copying the information, and then they're trying to perform the pointers operations, point operations, pointwise operations, like this one, multiplication and then the addition. Okay, that is what the output state or new state is generated. The out of that addition and t-1 in the addition of xt is now giving you a alternate state or new cell state, where you will get a updated information at that time. Okay, so try to understand what is happening over here. In this case, now they are trying to perform the multiplication. Okay, multiplication task. So what kind of multiplication? So why they're doing the multiplication? Try to understand these things. We have seen that in convolution neural network, if you could remember, whenever we trying to talk about the neural network, at that time you might have seen also the architecture of the Google Net, right? Or Google Net, or let's say some sort of information like ResNet, right? In ResNet, they're having some kind of information or blocks. Okay, this is the blocks. These are the blocks. Okay, hidden state blocks, hidden neural networks blocks. And then whenever image comes in, they pass through this kind of blocks, and then we are getting the finally the features and the classifications. Okay, feature and the classification. Sometimes what happens is whenever we're trying to apply the filters, some filters may give you same result. Like if in the image, if I'm trying to apply filter, maybe some filters is giving me the same encoding of the face, and some filter is giving me the encoding of the some other object. At that time, what happening is, what I can do is, they suggested that entire trying to process all these blocks. Okay, I'll try to show you with the different color. Rather than processing all these blocks, what we can do is, whenever we are at this first block, we try to skip this block and we try to go to the next block. Okay, we try to go to the next block. Why? Because again, they are trying to give you same encoding, and in order to perform or create a new kind of matrices, right? Not dropout, guys, not dropout. In dropout, we're completely deactivating the things. So what they're trying to do is, they're trying to create a skip connection. Okay, kind of a skip connection. They're trying to entirely skip this block. Okay, skip this block and trying to pass these filters to next layer. And by using that layer, they will be able to achieve the next filtering or next features. Okay, so similar concept is, again, whatever similar concept is there in the ResNet, that similar concept is applied over here in the output gate. So if in the hidden state, if they say that there is no significant change, okay, no significant change is there in the hidden state, and the context change is not happening, maybe what you have to do is, you have to carry out the same information, skip connection toward the gradient problem. Same is used in VGG. Correct, guys? That's what they are doing. Skip connections, they are using that kind of concept of the skip connection, that skip blocks. Okay, skip blocks or skip connection, where we are using the ResNet or Google Net, we're trying to skip some connection, and we're trying to pass the information to next block in order to remove the complexity as well as the problem. Okay, so and to achieve the next kind of features, okay, which will be different from each other, right? So what we have to do is, we are trying to process the sequential data. Now we have to understand that whether there is a change or not. In forget cell and input cell, we are trying to combine the things, and we are trying to update our memories. Okay, time by time we are trying to update our memory, and we are trying to understand what to carry, what not to carry. Okay, till the end. So we will be able to understand or construe entire the speech, right? That's my entire advantages of this LSTM. For that purpose, in output gate, I'm trying to apply this kind of concept or the ResNet. When I'm trying to skip some information, whatever meaningful information is not there, I'm trying to skip that information. Whatever information is meaningful, that I'm trying to do by using the pointers operation. Okay, pointers operation. So forget gate, see this forget gate into again the output of CT minus 1 plus into I into T into C into T, CT, right? So this is what they are trying to do. I will try to tell you what is actually happening. So main agenda, what is happening over here is, they try to understand what is the meaningful information, whether there is a change, no change or change, and that they try to decide, okay, on the basis of this information, cell state, whatever cell state is there, okay, that cell state, they are trying to apply this forget gate along with it, and on the basis of that, they are trying to create this kind of a matrix, this kind of a multiplication matrix. On the basis of that, they're trying to understand whatever encoding is generated. Let's say if there is meaningful info generated, then they will try to, or whether there is no meaningful information generated, this kind of operation they are try to perform. If 1 multiplied by 0 will become 0, that means they are trying to forget everything. And if not, they will try to create something like that, 1 minus 1 or 1. Okay, and then they try to perform the multiplication based on the changes. Okay, based on the changes and based on the meaningful info. Okay, this kind of pointer operation they are trying to perform along with whatever is carried until now within the cell, which consists of the forget gate information and along with the input gate information. Okay, all these things are now passed along with this kind of multiplication operation, and then on the basis of that, they try to filter out and try to update this memory cell. They're trying to update the memory cell with the final output. Okay, with the final output. That is what is happening in the output gate. And why we are trying to understand all these things, or why we are trying to do these things? Because we want to understand whenever there is a meaningful information, please retain that information. Please retain that information. If there is no significant change, then don't do any changes. Just forget the past information. Try to carry out the current state. Okay, that is what is entire things is happening. That's how the entire output gate is working. And then on the basis of this output gate, in addition, we add matrix of sigma 0 and 10. Yeah, guys. In addition, we are doing this, right, in input gate. But in output gate, they are trying to perform not a addition operation, just the multiplicative operation. You see this one multiplicative operation in the output they are trying to see, and then you will be seeing in the end, right? This is multiplication operation they are to perform, and then they are also using tanh. If you see there, they are also using tanh somewhere here. Okay, on the basis of that, they are trying to generate CT equal to 1 or ST. Right? So on the basis of 1, tanh is for 1 and sigma is for 0s and 1. So we are not using any sigma here. We are just using the tanh information. On the basis of the tanh, they are trying to understand the meaningfulness, and then they are trying to update the information. Okay, this is the output gate, AND gate, along with this multiplication. Okay, this multiplication of the forget gate and the tanh operation. They are trying to understand the meaningless of filtering, and then final state is updated there. This operation you are talking about, right? This is for the cell state, guys. So what after the output gate also, right? After the output gate also, when we are trying to filter the information based on the context and meaningfulness, right? Meaningfulness, that has to be again updated in the cell state. That's why there is a plus operation, okay? In the end, plus operation, and then this is able to achieve the final output. And this will continue, guys. This will continue until unless we achieve all the things. I think, guys, we have spent a lot of time understanding these things. So let's move to practical implementation. I will try to show you practical implementation. Much of the things has been discussed. Before we go, guys, I will also try to tell you what is gated recurrent neural network and what is the difference between gated neural network. Okay. So what is happening is, we have seen now what is the LSTM neural network. There are two benefits. There are two benefits when we try to update. LSTM is further updated. LSTM is further updated with GRU, gated recurrent neural network. And what is the advantage? Try to understand the advantage, guys. It is again, the use case is same. We are trying to process the sequence to sequence data, text data, and everything. But what is the advantage? That memory size taken is less in the GRU, and also it gives the speed. It gives the speed. Okay, and then it is also try to give you a hidden state operations, hidden state skipping operation. This kind of operation, these are the advantages why we use, and it reduces the complexity somewhat. It is trying to reduce the complexity also. We have seen like 4 kind of gates are updated. On the basis of that, they are trying to perform the operation, and then we are getting our final output, right? And in order to update that, they have introduced this kind of things: update gate, reset gate, alternative state, and new state. Okay, in controls composition of the new state. Yeah, guys, attendance link will be shared by a colleague. Okay, don't worry. So try to understand very important things. GRE is also gated recurrent neural network. This is the updated version of the LSTM, which gives the benefit of performing skipping of the hidden state, as well as the, yeah, guys, it depends. Whenever we trying to apply the faster thing and less memory application, GRE is used. Otherwise, LSTM is used mostly. Okay, I understand. What they're trying to do in GRE is, they are performing same operation, but they are doing some kind of, let's say, all this like forget gate, input gate, and output gate. Now they are clubbed with only 3 states. Out of 4 states, they are clubbed with the 3 states over here, and that they are trying to understand that how they are trying to adopt this new mechanism, using which they will be able to improve the memory, and they will be reduce some kind of closeness. Okay, they are combining, right? They are combining the cell state and hidden state in the LSTM as a single state. Okay, and then they are substituting this input and forget gates with the updated gates. Okay, update gate. Then they are combining this hidden state and the memory state with a single state, which is reset state. and then alternative state and new state. That's what they're trying to do. Okay, I'm not going to detail because there will be much time required. And then next thing will be like sequence to sequence. Okay, so whenever we're trying to understand what is sequence to sequence, I will try to tell you what is sequence to sequence. We are giving input as sequence and trying to find out sequence as our output. That time it will be helpful. And also there are certain flavors. Whenever we try to understand these things, people say that one-to-one, right? One-to-one, one-to-many, many-to-many, one-to-many. This kind of recurrent neural networks are there. These red colors are nothing but the inputs. These greens are nothing but the RNN cells. Okay, RNNs. Greens are the RNNs, and these blues are outputs, guys. These blues are outputs. Okay, so this is how the one-to-one, many-to-one, all this kind of you might have heard, right? Might have heard this kind of flavors with the one recurrent neural network, sequence learning with one recurrent neural network, or one-to-one. One-to-one means this kind of things. Okay, one-to-many, many-to-one, and then many-to-many, different combination. Okay, and nothing, same thing, guys. It is trying to do same thing, but with different combination, or how we trying to stack the things, or how the architecture has been built, and whether we are trying to generate the things, how the sequence output, right? Try understand this way. Sequence output, right? Image captioning, take the image and give a sentence of the words, right? Out of image, we are trying to create the sentences. Or sequence input, sentiment analysis, right? Positive, negative sentences. Or sequence input and sequence output, like machine level translation, right? That's what I'm saying, many to many. Many to many example is like, I'm trying to give a German and trying to translate it to English. Okay, machine translation, that is many to many. Sequence to sequence, right? Sequence to sequence generation, that kind of architecture. Very, very important concept, guys. Try to understand. Basis of the different kind of things we are trying to generate. There are this kind of neural network architecture, RNN architecture are used. Okay, or sequenced input, and the output is like labels. We are trying to labeling the various video frames. Okay, video frames. That's how the one-to-one, many-to-one, one-to-one, or one-to-many, this kind of architecture are there. Okay, and in sequence to sequence, guys, always we try to understand about the bi-directional RNN. Also, I will try to explain you within 5 minutes. Okay, what is bi-directional RNN, and in sequence to sequence, we are talking about the encoder-decoders. Okay, encoder-decoder, this way, encoder and decoder model. Encoder encodes, and then we try to decode the things. All these things I will try to discuss. Okay, give me like 5 minutes. First, I will try to show you the implementation. Okay, let me stop this one and show you the implementation using the LSTM, which is very beautiful implementation. And then we'll try to go back to these things very quickly. We'll try to finish this one. Not this one. Okay, wait. This is about the auto encoders that we'll try to discuss afterwards. Okay. So here I'll show you LSTM implementation. Right, guys. Just quickly ping me that you are able to see my Jupyter notebook, so I can go ahead. Okay, I can go ahead. We need to discuss very important topics as well. What is bi-directional RNN? Simple 5 minutes concept, and that's so I'll try to show you encoder-decoder model. First, I will make a quick walkthrough for this LSTM, and I will try to show you the time series data as well. So understand what we have to do is we have to bifurcate the things using the or let's say we are trying to bifurcate the fake news along with the real news. Okay, and we are trying to achieve this using the LSTM neural network. So I will not go into detail, guys, which are the steps we have already discussed. So what I am trying to understand is I will try to show you the architecture, how the LSTM will look like. Okay, that is very important. Otherwise, all the steps like importing the data, processing the data, word embedding, everything is same. Okay, so main architecture is different. How we should apply the LSTM, that is very important. Okay, try to concentrate, guys. I know so things are important like attendance and everything, but still we got an half an hour. So which is a very pretty good amount of time where I will be able to show you what is bi-directional LM, what is encoder decoder, and then how we can do a LSTM neural network or stacked LSTM. Okay, So try to understand. Very important topic, very important topics, guys. Try to concentrate this one. So if we are able to cover these things, then we'll be mostly covered with the 70% of the NLP topics. Then. All right. So without wasting time, let's go ahead. What we try to do is we are trying to make a fake news and a classification using the LSTM, or you can do a spam classification. You can do a generation text generation or image captioning or something like that. Okay, I'll try to discuss this thing. So what I've done for that purpose, I have taken this data frame, fake news data from the Kaggle, and try to import this data. This is how the data will look like. I will have a title along with author and the what is the text and what is the label, like whether this is fake or not fake news. Okay, this is what kind of a data I am trying to import. Then I saw that there are 20,000 rows and 5 columns. Then you just try to check the drop NA, is there, clean the data, something like that. Okay, and drop some label which are not required, like IDs and all. This is not required, right? Then I trying to check the data. Then the main thing, guys, once I am trying to import the things, then what I have to do is embedding, right? Like we discussed entire embedding technique, how the embedding layer will work, how we'll do padding, how I will be able to convert them into the 10,000 dimension by using the feature dimension to like say 10 dimension or 8 dimension, something like that. So that's what I'm trying to do. I'm trying to perform the word to vector over here using the embedding layer. Same things what we have seen, sequential function and everything. Okay, but only change now here is now I'm trying to import LSTM and also the dense layers, because I in the end to perform the classification I will require also dense layers. That dense layers means artificial neural network, normal flavors, and then I will also require a LSTM along with it, right? So first thing is vocab size, we already discussed. Then create a one hot encoding representation, and then by using this embedding layers, we'll try to convert them into the feature representation. Okay, so that's what we'll be doing in next steps. So this is what the data looks like. Then I am creating the stop words, then stammers. Okay, lemmatization, everything we will be doing. Corpus, cleaning the data, one hot representation of the data. Now I am trying to convert using the one hot representation. Okay, so once I am able to do one hot representation, then I will be calling the padding sequences to pad the data and then make it a same length, and then this data will be passed through the sequential layer for creating the embedding. Okay, word embedding. Once now guys, this part is very important. Within 5 minutes we'll be able to finish this code. That's not a difficult code. Now all the steps which are discussed now, we have discussed 2 to 3 times remaining things. Now this is new, and try to understand this very carefully. Now what I have to do is, first I have to create an embedding feature, right? Embedding a feature representation. Now I've taken a 40 embedding. Okay, 40 dimensions out of this 10,000 dimensions. Now what I have to do is same thing. We have to call a sequential model, and then I'm calling this embedding layer. In the embedding layer, we understood what is the max length, what is the embedding feature set, one hot encoding, and what is the vocab size. Vocab size was like 10,000. Max length, like what did we given? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and 11. Let's say this is max length 11. This is what the embedding is done like in the 11. And then what is the dimension I'm trying to achieve is 40. That's what the information I'm trying to pass over here, right? Embedding feature vector, maximum length size, and then the vocab size. And then what is the embedding is there, that data I'm trying to pass. And this will be able to give us a representation like we've seen, right? This in embedding presentation within this layer, right? And that will be now passed by to the LSTM. Now we are calling LSTM function. LSTM in background will be able to call a recurrent neural network with log short-term memory. Okay, and that to 100 neurons I am calling. Okay, 100 neurons. It consists of 100 neurons. That's what the simple layer I'm trying to call. And then once I am able to pre-process this data, whatever data pre-processing is done, that will be stacked and sent to a dense layer. And within that dense layer, I will be having a sigmoid function, which will be able to give me a binary classification, whether this news is fake or not fake. Okay, this is what the architecture look like. That's why I'm calling again, along with the LSTM, I'm calling a dense layer of one input, one neuron only, one neuron, which will be able to give me a 0 or 1 by using this sigmoid. And then model.compile, where I am trying to understand what kind of loss function I am taking, binary cross entropy, because this is a binary classification. If this would have been a multi-class classification. Yeah, guys, attendance link is already shared in the chat box. Okay, so binary class classification, that's why we are taking binary class classification, cross entropy. Otherwise, we would have taken sparse cross entropy. Okay, and then optimizer Adam and matrix accuracy, and then model.summary. Okay, that's how. This is how we'll be able to create our LSTM neural network along with the dense layer and along with the embedding layer. Okay, embedding layer also we have seen. Yeah, guys, my colleague will keep on sending after 5-10 minutes. Okay, don't worry, attendance. Okay, so what might consist of embedding Keras layer, then LSTM layer, and then my dense layer. Okay, dense layer. This kind of architecture is there. Okay, try to understand here. Embedding LSTM dense, 100 neurons of 40 dimensions. Okay, that is the parameter it is generating, and then last is 1 neuron. Okay, so that's how. And this is the 20 length, guys. Okay, don't worry about it. And then when I'm trying to see a shape, guys, vanilla flavor or simple LSTM. Yeah, you can see simple LSTM. We also have a LSTM like stacked LSTM. Okay, stacked LSTM is there also. Whatever vanilla flavor or naive flavor I was using for the recurrent neural network, and this recurrent neural network is updated by LSTM and GRU. Try to understand. Okay, so this is a updated version LSTM. Now we in LSTM also we are having a stacked LSTM where like we will be having our 2 recurrent neural network together working. Okay, that kind of things. So try understand this one. And then when I am trying to pass this data, split and train the model.fit, this is how the training will work upon. Then whenever I try to achieve this accuracy, okay, then even after achieving the accuracy, I see that I'm not satisfied, I can use a dropout layer. So I'm using dropout layer as a 30%, guys. Try to understand. I'm trying to add a dropout layer even afterwards in order to improve. After embedding also dropout, after LSTM also dropout, dropout 0 to 1, 3. Dropout is always between 0 to 1. 3 means 30% dropout I am trying to use. And then I am trying to rerun my model, combine my model and run. And then I am trying to check my accuracy. This is how the production grade will look like. And then if I check my accuracy, guys, okay, check my accuracy, I'm able to achieve a 90% accuracy. And this is the entire classification report which has been printed. Okay, this way we'll be able to analyze the fake news. Now switch back to next thing. Okay, I'll try to show you one more after fake news classification. Not bi-directional. Okay, I'll try to show you one. Stock market prediction. How the data will look like using LSTM. Next one. Quickly, we'll try to make a code walkthrough. So you guys will be able to understand not only text data also, but the time series data, how it can be used using the LSTM, stacked LSTM this time. Okay, we are taking a stock market prediction. Now I'll not go into detail, guys. This is the stock market share data which has been taken. This has been generated using the API key. Okay, and this is information like this one. Yeah, guys, I will be sharing all this information. Okay, notebooks and everything. So this is high volume, low volume for adjacent, all these kind of things you guys already aware of, right? Whenever I'm trying to look at the data, then I will be trying to look at the prices. What is the high price? What is the low price? When is it touching high? What is the volume traded on that day? Or everything. That kind of data is there. Then I will be performing some kind of a cleaning on this data. And then I will try to check the Try understand, guys, that LSTM are sensitive to the scale of the data. That's why we have to apply min-max scalar standardization. Okay, standardization of the data. That's why I'm trying to apply the standardization and feed the data into standardization. Whatever my original data was there, right? Then I'm trying to bring them into this kind of scales, right? Using the standardization. Then once I'm able to do it, I'm able to bifurcate the data and create a train and test data, right? And once I create a train and test data, then I will be calling my model. This model is important, guys. Try to understand now. I told you in previous example, when we are trying to perform a fake news classification, we are using single layer. Now we are using multiple stacking of the LSTM layers, and the same thing we are trying to use. Now we are not using any embedding layer because our data is already a time series data which is in the numericals. Okay. Simply I will call model.add LSTM 50 neurons and then return sequence equal to true, input shape this one. Retains sequence to that, all the other things can be understood later on, guys. First, try to understand the architecture. Okay, how, if you want to deal with the sequential data, that is the time series data, how you'll be using LSTM. So then second layer, I am trying to stack upon it of 50 layers, 50 neurons, and again third layer. Okay, and then there will be dense layer because I need to perform the regression, right? I want to understand what is the price, and within that I am taking a single neuron, then mean squared error and optimizer. Okay, this is how the entire architecture will look like for this stacked LSTM. And this is what it will be giving you: LSTM, dense layer, one neuron. This is 150 shape. Okay, and these many parameters, like 50, total 50,000 parameters are generated. Okay, and then we try to fit the data and we'll try to perform 100 epochs for the batch of 64 and try to understand how our loss is reduced. Yeah, I will try to tell you guys afterwards what is written sequence. We don't have much time. Okay, so once I am able to run the things, I will be able to predict the things. Then I'll try to import a mean square error. Okay, this is the mean square error, and then on the basis of that, I will be able to look at the graph, how the data is able to generate and how it will be the output. Okay. And whatever data is plotted, now they are trying to predict the next data, guys. Trying to understand. Till now, this one is our original data, and this is the prediction which has LSTM done. This is the prediction which LSTM has done, and they try to show it graphically. Okay, this is how the things will work. You guys can go through it afterwards. Okay, and try to understand what are the operations they are trying to do, because this is the predictions. Based on that, they are trying to understand these things. Okay, not straight, guys. When you will try to understand, go in the detail, then you will be able to understand these things. Okay, so they are trying to model predicting the models and then trying to plot the data. So that is not straight. If you look at it carefully, it is not straight. It is trying to show you variation. Okay, understood, guys? Now how we can stack the data. Now the next question is to understand what is sequence to sequence architecture and what is bi-directional LSTM. So I'll try to show you what is bi-directional. Within 5 minutes, guys, you'll be able to understand what is bi-directional LSTM, and I'll try to show you implementation next session. Okay, next session is totally dedicated, I know, for GPT, but I'll try to show you bi-directional LSTM. Bi-directional, which is a very beautiful concept, bi-directional LSTM. I try to discuss within 5 minutes what is this bi-directional LSTM, what kind of project we can create using CNN. Guys, CNN is used for the image classification, segmentation, image tracking. Okay, we're trying to perform a convolution operation using the CNN, and then we try to classify. Either we need to classify the image or detect the image, detect the objects, detect segment objects, or perform the tracking. That kind of operations are done using the convolution neural network. And LSTM, recurrent neural network, we are trying to process the sequential data. Now everyone understand what is sequential data, right? We are giving text, or we are trying to deal with the time series data. We are generating either text or we are trying to generate text. We are giving text and we are trying to generate the text. That is word prediction, next word. Okay, we are giving sequence or giving image. We are trying to understand the captions, or we are giving videos and then I am trying to generate a summary for that video. Okay, it will be able to understand that kind of things, or machine translation. Yeah, guys, you can use the reinforcement learning also in the forecasting. Okay, and now what we're trying to do is, when we're trying to perform a machine level translation, right? Translation from language to language, then I am giving a sequence and also I am trying to generate a sequence, guys. That is important. Okay, so now try to understand the concept of bi-directional LSTM. Very simple concept, but yet very powerful concept, guys. Now, if you have understood what is LSTM and what all, so let me draw a simple example and try to give you an example and what is the use of the bi-directional LSTM. All that things I will be able to tell you. Okay, let me draw a simple diagram. Let's say this is our LSTM cells. Okay, these are our LSTM cells. Let's say these 4 cells. Okay, these are LSTM cells, and for this LSTM cells we are having input. Okay, x1, x2, x3, x4. Now we are talking about bi-directional LSTM, guys. Bi-directional LSTM. We understood LSTM, which consists of memory cell, forget gate, then input and output gate, which consists of the entire LSTM. And then we are trying to understand that what is bi-directional LSTM. Let's assume that this is how the LSTM looking like, right? Looking like, and obviously it is try to generate an output also. I'll try to show you very quickly. Within 5 minutes, you will be able to understand what is bi-directional LSTM. It is trying to generate like this one, Y11, Y12, and Y13, and Y14 output. Y is output, X is input, 11, 12, 13, and 14. Okay. And this is the previous inputs. Okay. We are getting previous inputs required to T minus 1. And this is what the output one is there. This is what generated. Okay. So I understand that. Now what we are trying to do is here is in bi-directional LSTM. Let's imagine that whenever there are two outputs, output length term and short term memory, to output long term. Okay, guys, try to understand. Okay, try to understand what I'm trying to do here. Whenever we are trying to deal with a use case, okay, try and understand that. Whenever trying to deal with a use case, or I'm trying to perform such a thing where there is a dependency. There is a dependency on the future words. Okay, future words. At that time, I'll be using bi-directional item. How dependency on the future words? Try to understand. If I'm saying he likes eating, okay, maybe apple, fruit, banana, something like that. Okay, cake or plum cake, something like that, or any kind of dish, right? And then we have to understand what is the future word. Okay, future word. Then he likes eating. Entire context depend on the future word, right? Depend on the future word. So if I am trying to generate this kind of a sentences, and if I get an input of the future word well in advance, right? Or if I try to create any kind of sequence which will be able to give us a future word connection, so I will be able to generate in a better way. So I will be able to create a good understanding of the future words, right? So RNN is not giving this kind of things, right? RNN is not giving this kind of things where we are trying to provide a future input also. Till now, what we're doing, we are giving this old inputs, old outputs as an input, and then we are adding new input, right? Till now. But what if at the level 3 only, let's say at the level 3 only, if I'm trying to give an input of 4, so that will be amazing, right? Whenever I'm trying to read a future word. For that reason, we are trying to understand these things, that he likes eating plum cake or bananas or fruits or any sort of dish, right? For that purpose, he likes the barbecue or that kind of things, right? So in order to perform that, we need a bi-directional LSTM. And what is the main concept? I'll try to tell you here within a minute. Okay. So whenever I am trying to solve any use case which require a dependency on the future word, or let's say I'm trying to create a sentence that the bank is. Now, by using only bank is, I am not able to understand the context, right? So if I use the end word, the future word, that is called as robbed. Bank is robbed. Then this is giving me entire information, right? That means I have a dependency on the future word, right? I have a dependency on the end word. So I'm trying to predict the end word at that time. For that purpose, I require this kind of bi-directional LSTM architecture. And then what is the use or what is the change in this bi-directional LSTM is, guys, I will try to upload all these things. Okay, today, don't worry, try to understand the things. So what I am trying to do, only change over here is now I am trying to create a, in between this, I am trying to create a new cells like this green one, new blocks. Okay, new blocks, which will be giving us a connection. Okay, a connection. In between these blocks, I am trying to create a new blocks this way. And this is giving a backward connection. Okay, guys. Now, obviously, for them, there will be outputs. There will be output for these green blocks as well. Okay. and try to rub some things so you guys will be able to understand it. Okay, try to understand this, guys. Very important. In bi-directional LSTM, what I am trying to do is, when I created LSTM architecture, in between I am trying to create a new architecture within this LSTM, and then I am giving a backward connections like this one, these connections. So what happening is, this connection is not only now connected, whatever this LSTM connection is there, not only connected with this one. Let's take example of X3. Now this X3 is also connected with this bi-directional LSTM of reverse direction of this X4 also. That means I am getting a future reference also along with this processing, right? Till now we are getting only, try to understand it in this way. I am getting output of H t minus 1, H t minus 1. And now I am giving output of X, input of xt, and then I am trying to pass it in the neuron, right? So what I am trying to do is, here at x t plus 1, this kind of output is also I'm trying to give. This kind of things are happening now, okay, in the bi-directional LSTM, and this is happening in reverse direction, guys. And try to understand that this is different from the back propagation. This is not the back propagation. We just trying to do a reverse. We're trying to do a reverse thing, okay, reverse direction. Okay, two LSTMs are working simultaneously, stacked with each other, and this green one is also LSTM, and the red one is also LSTM. But one LSTM is going forward way, and one is going back direction. Okay, back direction, and they are giving the inputs. Okay, why we are giving input? Because sometimes we require the future prediction. That's how. Okay, that is called as bi-directional LSTM. And why we are using bi-directional LSTM? Because there will be, and when we are using this kind of task is for the NLP purpose, where we have a future dependency. If I use the normal LSTM, normal recurrent neural networks, okay, recurrent neural networks, RNN, that time there will be like problem, like in speech recognition, right? In speech recognition, or right in the where the complex architecture is there, at that time this bi-directional LSTM will take too much time, because in speech recognition, if I am having lot many words and trying to perform all the operation like forward and backward, it will have an issue. But when I am trying to understand that there is a dependency on the future task, at that time I can use the bi-directional LSTM. Okay, bi-directional LSTM. So there are also advantage and disadvantage of this bi-directional LSTM, guys. Okay, try and understand. Then last concept, guys. Last concept I want to tell you. I know it's a time, 5 minutes time, but that is more than sufficient. Like 4 to 5 minutes, we'll be able to understand what is sequence to sequence model. I understand, guys. Sequence to sequence model. Sequence to sequence model. Disadvantage, I already told you guys that these bi-directional LSTMs are very slow. Okay, very slow, and they create a complex structures. So when we're doing a speech recognition or something like that, at that time they will be working very slow. That is the disadvantage for them. And there is a speed issues also there with this bi-directional LSTM. Now in short, if I want to summarize what is bi-directional LSTM, this is a two-way communication happening, and we are having a future dependency. Then I am trying to give a future word to my current state only, and then I am trying to build a model so which will be able to perform a very robust way. Okay. Now sequence to sequence means what? Sequence to sequence understanding is that it has been trying to understand this way, that it was developed by Google in 2018. Okay, for the machine level translation. What do you mean by machine level translation? Is that if I am trying to perform any speech recognition, and then I'm trying to convert the speech to another speech. Okay, at that time what I have to do is, there are two types of networks which will be working. Okay, one is called as encoder, one is called as decoder. What encoder does is, it try to extract the information and encode it in the hidden state. Okay, something called as hidden state. My encoder, what it does is try to extract the information and find the semantics and try to encode it in a hidden state. Okay, this is called as hidden state, and this is my recurrent neural network, one layer. Okay, guys, try to understand it. Very simple and yet very powerful, because whenever you are trying to perform sequence to sequence translation, I told you, right, like speech to speech, speech recognition, this kind of things, that input is also sequence and output is also sequence. At that time you will be getting this kind of architecture, and I will try to show you amazing use case of the encoder decoder model. I will try to show you this use case also, not today, But in tomorrow's session, within 10 minutes of time, I will try to show you what is a beautiful, amazing real-time use case of this encoder-decoder. Try to understand this context of the encoder-decoder within 5 minutes, and then we'll be able to stop for the day. Okay. So try not to ask question, try to focus for next 5 minutes, guys. Okay. I will not take much of your time. I understand that we have a limited time. So try to give attention to this topic. So when I'm saying that sequence to sequence model means what? My input is also sequence. Okay, and whatever output I'm trying to generate is also sequence. Okay, this is the first thing. Then sequence to sequence model, what is happening? In the background, they are using RNN only, recurrent neural networks. Okay, again, this is a one kind of architecture. How we can form architecture of the recurrent neural network. We have seen LSTM. We have seen LSTM. This is a one more flavor. We have seen GRU, get a recurrent neural network. We have seen now bi-directional LSTM. What is happening? Now there are different use cases, but if I try to arrange the recurrent neural network in such a way that I will be able to process a sequence to sequence data. And how it will be done is using this encoder and decoder. What happens is first part is called as first neural network, which is again a RNN neural network. That will be a same thing, guys. We are trying to look at the same thing, whatever neural network we are seeing. But since understand that this is called as encoder. What the work of the encoder is to extract the information and code it, perform the encoding. Once this information is extracted and encoded in the hidden state, then there will be another parallel network, recurrent neural networking, which is called as decoder, right? And decoder, what it does is whatever information is there in the hidden state, will try to understand and decode the information, decode that information, and then it will be able to generate the sequence. That's what the architecture looks like. So let's go and understand. Very fast, within couple of minutes, try to understand what is encoder decoder models. Examples like image captioning, sentiment analysis, whether person is positive, negative, or whether person is laughing, whether is happy, not happy, that kind of thing. On mainly into the machine level translation, like Spanish to English, English to German, German to some other language, right? That kind of things. And if you want to understand, guys, how the encoder decoder working, very simple example is like Pictionary. Okay, try to understand what is Pictionary. In Pictionary, what happens is whenever we try to play this game, just like the dumb charade, one person, player one, what he does is he try to draw a diagram, and whatever diagram is drawn, second person is trying to guess that diagram. Okay, so first person is called as encoder. Then this diagram is called as hidden state, and then second person, whatever is guessing, is called as decoder. Okay, decoder. That's how the things work. Whenever I am trying to convey any message, okay, player one, what he does is he try to create a picture. On basis of the picture, I can see this picture belongs to a rabbit. Okay, so I will understand that, okay, it is a rabbit. Someone may say it is a cat, it is a dog, right? Depends on the accuracy, right? And they will be able to guess it. Once you are able to guess it, what accuracy you are trying to guess it, that will be your recurrent neural network's performance. Okay, that's how the things will work. Let's understand in the terms of the machine level translation how the things will work. Let's say in machine level translation, I am giving this word. Let's say I am trying to give a word Ich bin Vikas. Okay, that means my name is Vikas. This is German word, Ich bin Vikas. Okay, so what will happen is recurrent neural network, we understood, it takes word by word, it tries to process the things, then it will try to give you output, right? And again, the weights are coming this time with respect to the time t, at time t minus t0, at t1 and t2, right? It will try to take one word like Ich bin Vikas, then it will try to perform all the operation, recurrent neural network operation, like going from the sigmoid function, weight addition, multiplication, everything, and it will try to decode the things, and it will try to create one kind of vector. Okay, that is called a hidden state. Now this will be given to decoder, and then decoder will again try to take one word. Now what I have done for each, I have created one encoding. Let's say this kind of encoding is there, number encoding. Let's say 10. For bin, I have taken encoding as 20, and for Vikas, I have created 30. And this 10, 20, 30, I have passed to our another recurrent neural network. Now recurrent neural network is doing work like from numerical to word. Numerical to word. What we did is word to vector. Now vector to word is happening. Okay, so it is trying to take this 10, 20, 30, and for this 10, 20, and 30, it is trying to say that I, Ish means I, then bin means 20 means I am, and then for 30 means Vikas. Okay, this is how the entirely the machine translation works, guys. Okay, this is the encoder decoder model. Understood, guys, how the encoder decoder works? So this, and again we have understood like recurrent neural network, how it is taking, how it is trying to convert the data, and how it will be able to perform the things, right? This encoding you understood now, word to vector, and then from vector to again word. This is what the two-step process happening in encoder decoder. Okay, yes guys, I think this much is sufficient for the today. I know there's a lot of concepts which you have spoken today. Tomorrow within 10 minutes, I will try to show you a practical implementation of RNN. Using RNN, how we will be able to understand the movie analysis. Okay, movie analysis. You guys were saying that I have not shown you the RNN, right? Simple RNN. This is how the LSTM look like and how the GRU look like. Okay, I'll try to show these layers, and then we'll try to do a movie analysis, movie sentiment classification. Okay, using the LSTM, and then I will try to show you also that how the encoder decoder works. In encoder decoder, I will try to show you a practical implementation that how I will be able to create a out of a blur image, how I will be able to calculate a high definition image. Okay, high definition image. That kind of implementation within 10 minutes quickly I will try to show you tomorrow, and then we'll try to understand entire all the session will be dedicated to GPT, guys. GPT model. Okay, what is the GPT? ChatGPT, whatever we understood. What is GPT? What kind of models are there? What is large language model? What are some applications? I will try to show you application. I wanted to show you guys that how we can build an application using the ChatGPT, or kind of a large language model which use the lang chain, thing. Okay, in the background, but it requires like $40-50 of subscription. I will try to find out if I get any implementation. I will try to show you like how you can create your own chatbot, using the ChatGPT, or how you can train your own data on the large language model using the ChatGPT. That kind of application we'll have to try to see, or maybe I will try to show you some simple application using the ChatGPT. And what is the ChatGPT? What is the architecture? How it is trained? All these things we'll try to discuss tomorrow, and that will be the end of the session, guys, for our NLP. I think we have covered all the 70 to 80% of the topics for the NLP. Okay, what is remaining is now transformer. Transformer again consists of the encoder decoder and the BERT and GPT. That's it, done. The GPT, anyhow, we are trying to understand tomorrow. BERT is nothing but is a bi-directional encoder representation for transformer. It is again a higher level architecture of the encoder decoder, which help in sequence to sequence architecture. Okay, so that means we are remaining only with the 20% of the portion. Try to cover that also. Okay, all right, guys, hope you understood. Okay, all right, guys, about the materials. Okay, don't worry, all the materials of the day 1 and 2 I have shared with Amar. I'll also try to share today all these things which we have discussed, all the practical implementation, time series data, LSTM, simple recurrent neural network, and the word embedding layer. Okay, all these 3 IPMBs also will be shared in the learning management portal. Okay, in ExcelR. And also, BERT and encoder decoder also. BERT is different, guys. BERT is for bi-directional encoder representation for the transformer. Encoder decoder is a simple model. Okay, that's what. All right, guys. Then I think we are already 7 minutes late, so I will try to conclude today's session. Okay, and I hope you guys have enjoyed. I know it is a bit more information. We have seen many implementations. So, but I guess that it was very exciting, very helpful, and you were able to achieve some knowledge out of it, right? So thanks, guys. I would like to conclude this meeting. If you have any feedback, please punch me for next 1 minute. Then I will try to close this session. Okay. Any feedback, any suggestions, any thoughts, okay, on today's topic, guys, quickly. And also we'll be having session tomorrow, guys, for the GPT models. Attendance link is again shared by my colleague. I hope every one of you have attended the attendance link and filled it. Okay, guys, quickly ping me. Did you enjoy this session? What you thought? Give me your feedbacks. Any queries? Anything else? Quickly, guys, 1 minute. Then we are already late, 8 minutes late. So I will try to close this meeting in the next 1 minute. Go ahead, guys. Punch in fast. What are your thoughts, feedbacks? Sentiment analysis, which is the best topic? Okay. Please suggest the research topic for LSTM. Okay, guys. I'll try to give you answers. Sentiment analysis, guys, always depend. If you are trying to perform a sentiment analysis, which is very complex, then always use LSTM, recurrent neural networks. It gives very high accuracy because you are using the deep learning models there. For machine learning, I told you, there is no sequence information. We are not creating any kind of sequence. We are not trying to have the memory cells. That's why we're doing sentiment analysis with the mostly LSTM and all. LSTM application and research topic I will share with you guys. Don't worry. What else, guys? Anything else? How to extract data from social media? That is again a different topic, guys. It is called as web scraping. Okay, web scraping we have to do, and there are also APIs which are exposed by the different like Twitter has API, Facebook has API, or even if you want to go to any website like let's say Open Weather Map, whether you want to understand the weather maps information of, okay, all that things, they have their APIs, and you have to do a web crawling, web scraping. By using that, you will be able to download. What about the bird search? Yeah, but guys, we'll try to understand. Not much time we are having. Actually, we want to discuss the ChatGPT, and also I want to show you two implementation for this encoder-decoder model and this one, sentiment analysis, movie sentiment analysis using the LSTM. So I doubtful about the bird. Okay, maybe in coming series, we'll not stop here. We'll be having some upcoming series as well. At that time, maybe we'll try to cover these topics. All right, guys. Anything else? I know it's late, 10 minutes late. If no major topics, no major queries, can I assume you guys enjoyed this session? Right? Innovative session, informative. Sorry. Quickly ping me, guys. All right. All right. All right, guys. Then if no further information, no further questions, no queries, then I hope you enjoyed this entire session. And thank you very much. And see you tomorrow. Last session, guys, tomorrow. Very innovative session about the GPT models. Okay. ChatGPT model, high-end models. I'll try to see the implementation. Okay, guys. Thank you very much. And see you tomorrow, guys. Good day. Bye-bye. All right. Amar, please go ahead.
Yeah.
And thank you.
Yeah,
Thank you,
sure.
guys. Thanks.